Hi there, Mrs. Vance again. Today's lesson is about chemical bonds. We're on the second part of Chapter 2 or Unit 2, and we're talking about chemical bonds today. So, when we talked about the periodic table, we talked about the fact that the elements are in different periods on the periodic table. Okay, and the period is going to tell us how many energy levels or how many electron shells each atom has within that period. So remember, the periods are the rows. And so elements on the first row, as you see here in the lower right-hand corner, have only one energy level, or one shell, okay? You can call them either things. In chemistry, we usually call them energy levels, but your book refers to them as shells. And so the first energy level can hold up to 2 electrons, and there are 2 elements in that period that have that characteristic. In the second period, they have 2 shells or 2 energy levels, and so they can hold up to 8 electrons in that second level. And then the third period, elements in the third period have 3 energy levels or 3 shells, and they can also hold up to 8 in that outermost shell. Okay, and so each one of those electrons in those shells have specific distances from the nucleus. You'll learn more about how this works in chemistry next year. We're less concerned with those kind of interactions and more with how they form compounds. And so we're looking at how bonds are formed. When you have an atom whose outer energy level is not full, it has a tendency to interact with other atoms whose energy levels are also not full, and they can either share, gain, or lose electrons, forming attractions that we call chemical bonds. And so we're going to look at a couple of examples of types of chemical bonds that can be formed by various kinds of atoms. First of all, we're going to have a little question here. So when you look at the electron distribution diagrams for hydrogen, oxygen, nitrogen, and carbon, see if you can't figure out how many covalent bonds each one can form. All right, you should have been able to figure out that hydrogen has room for 1 more electron, so it can form 1 bond. Carbon has 4 electrons in its outermost level, so it has room for 4 more, meaning it can form 4 bonds. Nitrogen has 5 electrons, meaning it has room for 3 more, so it can form 3 bonds. And oxygen has 6, meaning it has room for 2 more, meaning it can form 2 bonds. All right, let's watch a little video about how covalent bonds form.
A covalent bond is the sharing of a pair of outer shell electrons by 2 atoms. For example, each of these hydrogen atoms has 1 electron in its outer shell, but needs 2 electrons to complete its outer shell. If the 2 hydrogen atoms share electrons, they can both complete their outer shells. The shared pair of electrons constitutes a covalent bond, shown in shorthand as a line. The covalently bonded hydrogen atoms form a molecule of hydrogen gas. A molecule is defined as 2 or more atoms held together by covalent bonds. An oxygen atom needs 2 electrons to complete its outer shell. 2 oxygen atoms can share 2 pairs of electrons. A molecule of oxygen gas is held together by a double covalent bond, 2 shared pairs of electrons. A carbon atom needs 4 electrons to complete its outer shell. It can share electrons with 4 hydrogen atoms, forming a methane molecule containing 4 single covalent bonds. Methane is a compound, a substance formed by the combination of 2 or more elements. We call methane natural gas. It is the fuel burned in gas stoves and furnaces. An oxygen atom needs 2 additional electrons to fill its outer shell. Thus it can form 2 single covalent bonds. An oxygen atom can share electrons with 2 hydrogen atoms, forming a molecule of water containing 2 single covalent bonds.
All right, so let's look here. In a nonpolar covalent bond, that means that the electrons are equally shared, okay? Those are called nonpolar covalent bonds. But there are also covalent bonds that are called polar covalent bonds, like the ones you find in water. In a polar covalent bond, electrons are pulled closer to the more electronegative atom. Electronegative means that it has a stronger attraction for electrons, and so the electrons spend more time around that part of the molecule, meaning that the bond formed between the atoms is polar. It has poles, like positive and negative poles, like a magnet. All right, here's another question. Polarity refers to a separation of charges. Think about the positive and negative poles of a battery or of a magnet, okay? So explain why the bonds in a water molecule are called polar covalent bonds. So in a water molecule, the electrons are more strongly attracted to the oxygen atom. It's bigger and has a much higher positive charge in the nucleus than the hydrogen atoms do. And so the electrons spend more time around the oxygen, making the oxygen end of the molecule slightly negative and the hydrogen ends slightly positive. And that makes the bonds polar because there's a negative pole and a positive pole on the bond. The other kind of bond, the second kind of bond we're talking about today, is an ionic bond. In ionic bonds, you have attractions between ions of opposite charges. Now, an ion is an atom or molecule that has an electric charge because it has either gained or lost electrons. It can gain or lose 1, 2, or 3 electrons, and so forth, okay? When you have two ions with opposite charges, they're going to have an attraction for each other. But remember, opposites attract, likes repel. When that attraction between ions of opposite charges holds the ions together, that's called an ionic bond. And you see the example in the picture here of salt. Salt is a synonym for an ionic compound, any ionic compound between a metal and a nonmetal. In the case of table salt that we use all the time, the metal is called sodium and the nonmetal is called chlorine. And so this sodium chloride is the name for salt, which is made of an ionic compound between sodium and chlorine. All right, here's another question for you. Explain what holds the ions in a crystal of table salt together. What is it that holds them together? And of course, the thing that holds them together is the attraction between the positive sodium ions and the negative chlorine ions that hold the atoms together in the molecule. All right, here's how that works. A sodium atom has 1 electron in its outermost energy level, as you can see here. A chlorine atom has 7 electrons in its outermost energy level. Since it's only got room for 1, if it takes 1 from sodium, that would make the chloride atom complete. Okay, like here you've got a full energy level. And now sodium also has a full outer energy level because since it lost that 1 electron here, it only has 2 energy levels and its second level is already full. That way both atoms have a complete outer energy level, and they are even though they have a slight charge, a positive charge for the sodium, a negative charge for the chloride. Positive for sodium because it now has more protons than electrons, and chloride is negative because it now has more electrons than protons. But that since they each have a charge there, they're attracted to and held together in an ionic bond. All right, now we have a video about ionic bonds.
Sometimes atoms complete their outer shells by stealing or giving away electrons. This happens between sodium and chlorine atoms. An electron moves from the sodium atom to the chlorine atom. The outer shells of both atoms are now complete, containing 8 electrons. The chlorine atom now has 18 electrons, but only 17 protons. Because an electron has a negative charge, the chlorine atom now has a net negative charge. Such a charged atom or molecule is called an ion, in this case, a negative ion. The sodium atom has lost an electron, leaving it with an extra proton, which has a positive charge. The sodium atom has become a positive ion. ions with opposite charges are attracted to each other, forming an ionic bond. These ions combine to form a compound with new properties. In this case, sodium chloride, ordinary table salt, is formed.
Okay, so just as a little bit of a review here, there are two main kinds of chemical bonds. First of all, an ionic bond, as shown in this cartoon here. One atom donates an electron to the other one, making them electrically attracted to each other. And the second kind is a covalent bond, in which they share electrons. The electrons orbit basically around both of the atoms, kind of like this. Okay? Covalent bonds can either be nonpolar, in which the electrons are shared equally between the atoms, or polar, in which case the electrons spend more time around one atom than around the other. The atom that they spend more time around is called electronegative, because it becomes electrically negative as a result of taking those electrons, or the electrons spending more time there. It's kind of stingy when it comes to holding on to the electrons. Now, there's a certain kind of bond that we spend a lot of time talking about in biology, and that's called a hydrogen bond. A hydrogen bond is a weak bond. It's not a molecule that holds a molecule. It's not a bond that holds a molecule together within itself. It's a bond that holds separate molecules together. It's very important. It's like it says here, one of the most important types of weak bonds. Okay, the hydrogen atoms of a water molecule are attracted to the oxygen. Attached to the oxygen by polar covalent bonds, and because those bonds are polar, and because of the shape of the water molecule, water is a polar molecule. Here you see the negative oxygen of one water molecule is attracted to the positive hydrogen of another, and the hydrogen is attracted to the oxygen of a different one. And so the water molecules are held together by these hydrogen bonds. And it's very important. This is why the reason that water behaves the way it behaves in a lot of cases. We're going to look at some examples of that coming up pretty soon. Here's another question for you. What is it that enables neighboring water molecules to hydrogen bond to one another? And of course, you should have answered the electrical attraction between the slightly negatively charged part of one molecule with the slightly positive charge of a different part of a different molecule. All right, let's watch a video about water and polar covalent bonds.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
So we also chemical reactions are involved in making and breaking those chemical bonds. You can have molecules that you can combine together to make other molecules. Sometimes, as in the case that's shown here in the white box, you have molecules of different elements, like hydrogen and oxygen, that can combine to make molecules of a compound like water. This is why you have to write chemical equations like the one you see here. When you have hydrogen molecules that you join together with oxygen molecule to produce water molecules. Remember, when this happens, the chemical reaction doesn't create matter or destroy it, it only rearranges it in different ways. And that's the purpose of having a chemical formula, a chemical equation, because it shows how those reactions occur. One more question before we end this video. We're asking you to look at if you can, or determine whether you can fill in the blank with how many numbers there are in this particular chemical process. The compounds here are glucose, which is C6H12O6, and oxygen, which is O2, and we're going to produce carbon dioxide, CO2, and water, H2O. How many molecules of each of those compounds or substances are going to be produced or used and produced in this particular chemical process? You should be able to tell me that if you add 6 oxygen molecules to 1 molecule of glucose, you're going to produce 6 molecules of carbon dioxide and 6 molecules of water. And that is the end of part 2 of Unit 2